Hi, welcome again to another video about chemistry. Hey, let's take a look at a couple things. Let's explore the three states of matter and physical versus chemical changes. Okay, three states of matter. Okay, well, three states of matter are simply gas, liquid, and solids. Sometimes we say the three phases of matter. We might talk about a material in the liquid phase, or hey, we got brass or aluminum in the solid phase. It's a state of matter is all. Pretty straightforward. Let's look at water specifically. Here on the screen are the three phases or the three states of water. You know them as ice, water, and steam. Got an Erlenmeyer flask here holding some ice cubes. And that's the solid phase of water. We got liquid water over here. Sure, that's liquid water in the third flask. These little vapors, these little trails, it's supposed to give you the feeling that, hey, the flask is not empty, it's filled with water vapor or steam. Oh, and a quick note about steam versus water vapor. Water vapor is just moisture in the air, humidity, right? Steam, we commonly think of water vapor, humidity in the air, but it's really hot. It's above the boiling point. Okay, I won't be too particular about how we use the word steam and water vapor, but if you hear me saying water vapor, think of it as just moisture in the air, humidity. Okay, on a chemical level or a molecular level, what's going on? Let's start over with the gas molecules of water. You may know water has a chemical formula of H2O. We'll explore that in a little bit. But right now, just realize that the smallest piece of water is this little chunk right here, which consists of an oxygen atom stuck to two hydrogen atoms, two H's, one O. Yeah, that's the chemical formula, H2O. Smallest piece of water that we know of. And when water exists as steam or water vapor, what's happening there is the individual water molecules have unstuck from their neighbors. They're freely bouncing around, lots of energy bouncing around in the gas phase. Now, if you cool them down, slow them down, well, it turns out water turns out to be a very sticky molecule. We'll use some more scientific terms to explain that later, but you could say it's a sticky molecule. So as you slow these water molecules down and they're bouncing around the gas phase, they tend to stick to each other. And as they stick to each other, they start to form little droplets of water. And a droplet of water is a liquid. The water molecules are now in the liquid phase when they're sticking together. Now, if you continue to slow these down, you continue to cool down the water molecules. Well, now they can freeze or form solid water. You know that as ice. What's happening on the molecular level? Well, the sticky portions of the water molecule, they have to do with the hydrogen to the oxygen linkage there, and that's kind of directional. So if you form ice and you zoom in on it, and you could look at the individual water molecules, you would see the H's of one water molecule sticking to the O, the oxygen, of a second water molecule. And to get the orientation right, see, it turns out, we'll discover later, that the H's tend to be on one side of the oxygen molecule. They're not 180 degrees apart. Because the H's tend to be on one side of the oxygen, and the H's like to stick to other oxygens, they naturally form these hexagon shapes. You can kind of see a six-sided figure here as you connect the oxygens of each of those water molecules. And yeah, and so that's the perfect alignment to get all the water molecules to be optimally stuck together. And it turns out if you ever look at a snowflake or see, under a microscope, if you see images of a snowflake, they all have this six-sided feature. They all have these six prongs, so little crystal barbs, whatever. They're all six, this six-fold symmetry. And it has to do with the fact that that's how water sticks together, in those little three-dimensional hexagons. Cool. All right. So take-home messages here. To change among the three states of matter, temperature is what you want to do. And temperature is proportional to the speed of the molecules. The hotter the temperature, the faster the molecules are moving. So if the temperature is low, that means low speed. These water molecules might be vibrating in place, but they're stuck tightly together as a solid. You warm them up, they have more heat energy, they have more motion, and they have enough motion to unstick from their neighbors to get out of this perfect arrangement and get into this less perfect arrangement where they're still sticking to each other, but they're moving, bouncing, scrolling around as a liquid, in the liquid phase. And if you keep heating them up, well, then they tend to just bounce off each other and eventually unstick completely as a single molecule. And they're completely unstuck from each other. And that's true for all the gases, right? That's what a gas is. It's individual molecules moving so fast that they collide with other molecules and they don't stick together. And the trick is, molecules are super, super tiny. They're invisible for the most part, right? So you shine light on them. The light wave kind of goes around them, doesn't bounce off of them, meaning we can't see them. So right now, between me and this camera, there's a whole bunch of air. I mean, you can feel the air molecules, but those air molecules are not blocking the view of the screen, right? The light is going right through those, or around them, I should say. Take-home message here, gas molecules are individual molecules not sticking together, and they're too small to see. Okay, cool. Let's see what else we got here. Melting point, boiling point. Right, so when you talk about the three states of matter, gas, liquid, solid, you can talk about changing the material among those three phases, right? So if you want to change a solid to a liquid, well, you melt it. Whether it's water, or I should say ice, you want to melt ice, solid to a liquid. You can melt, I don't know, lead, if you want to make something out of lead, or brass, you would melt it down, melt solid brass to liquid brass, right? Candle, take a hard candle, melt it down to liquid candle wax. You're melting it. And for each material, there's a specific temperature by which they melt. So just be familiar with the term melting point. We might abbreviate MP from time to time. And that's simply the temperature at which something melts. But hey, if you take some liquid water, put it in an ice tray and stick it in the freezer, it'll turn back to a solid. It will freeze. And what temperature does that happen at? The same temperature at which it melts, right? So the melting point is the same as the freezing point. And if you use the Fahrenheit scale, that's 32 degrees. If it's Celsius or centigrade, 0 degrees Celsius. Kelvin, we'll see Kelvin in a little while. Another way to measure temperature, 273 Kelvin's that number. You don't have to memorize these, but very helpful if you have 0 degrees memorized as a freezing point or melting point of water. And 100 degrees is the boiling point, right? So you know about boiling. You ever put some spaghetti on the stove, you want to get a pot of water boiling first? That's because the water is at 100 degrees as liquid water changes to steam. And the more heat you apply, doesn't matter. The water temperature doesn't increase beyond 100 degrees because all the heat you add is just helping the liquid water molecules unstick, jump up into the gas phase as steam. So the boiling point, another term you need to know. We'll abbreviate from time to time as BP, and that's simply a temperature at which a substance boils. That goes from liquid to gas. But of course, you can take that gas, take that steam, and if you slow it down, cool it down, it'll reform water. And the term for that is condensing. So take some gaseous steam, gaseous water, take some steam, cool it down, you'll condense it to liquid. So that's a term you should be familiar with too. When you talk about any gas, Take some gasoline at an oil refinery. They'll heat up the gasoline until it forms a vapor, and then they cool it down or condense it back to liquid gasoline. And they do that to kind of purify it, separate it between diesel fuel and gasoline and all sorts of things. We can talk about that another time. Okay. The other main topic of this video is physical versus chemical changes. Let's keep melting point and boiling point on the screen. That'll be helpful. So what is a physical change? Well, we got a general definition here. It's an okay definition. It's going to need some help though. A physical change is simply something that does not alter the chemical makeup of a material, a substance. And so we have a good example of that. Hey, if you melt something, if you melt water specifically, you take ice, change it to liquid water. What's the chemical makeup of ice? H2O. What's the chemical makeup of water? Liquid water, H2O. Yeah, you didn't change the chemical makeup when you melted it. Same thing as when you boil it, right? So right here at the top of the screen, we got little H2Os sticking together as a liquid. Heat them up, you boil it until it forms a gas, and now the individual H2Os are not sticking together. But whether liquid or gas, whether water or steam, it's still H2O, same chemical composition. That's a physical change. Boiling is a physical change, as is condensing and freezing. Okay, is that the only thing that's physical? No. What if you take a big old rock, a big boulder, and just smash it into a bunch of smaller rocks? No, that's a physical change. You didn't do anything chemically to it. It's just smaller pieces of rocks. There's a whole bunch of other ideas or other examples in the homework we'll get a little more familiar with. Right now, we don't know the chemical formula of rocks and boulders. It's not in our book, right? But you could look up minerals, and you could actually get the chemical formulas for that. So you take some quartz, I think that's silicon dioxide, SiO2, smash a crystal of quartz into smaller pieces of quartz, it's still SiO2. Yeah, so chemical makeup didn't change, it's a physical change. However, during a chemical change, you do change the chemical makeup, right? So going back to the candle, take candle wax, gently melt it to form liquid candle wax. That's a physical change. If you gently heat up the wax, you're trying to boil it, that could be a physical change, but hey, it'll probably catch on fire first. And now, what's coming out of the flame? Carbon dioxide, maybe some soot. Okay, that's not candle wax. That definitely has had its chemical composition changed. So burning is an example of a chemical change. You're changing the chemical makeup of the material. It really helps if you have the chemical formula, so you can see if the chemical formula is the same before and after. So was it water, H2O before? Is it still water after? If so, it's physical change. If it changes, then if the chemical formula changes, it must be a chemical change. I should be a good scientist here and define my terms. So on the screen, I do have a definition for a chemical formula. It's simply the listing of the type and number of atoms that make up a substance, right? So water is H2O. Here's the formula explicitly written out. H subscript 2, capital O. The 2 belongs with the H, saying, hey, there's 2 H's, 2 hydrogen atoms. That's 2 atoms of the hydrogen type. And there's a single O, that's an oxygen atom, a different type of atom. That's what makes up water. 1 O, 2 H's, 1 oxygen, 2 hydrogens. One of those gas molecules we exhale is a waste product, carbon dioxide. 1 C and 2 O's. So here's a chemical formula, CO2. Cool. Let's see, what else we got here for you? We've got a quick little example over here. Let's say we put some water in this container, add a little acid. Don't worry about the acid, it just helps the reaction go a little faster. And this liquid water, we're going to connect to a battery. I know it's just a little schematic of a battery, but this is the battery. It's some wires, and there's a metal plate at the end here. We've got some chemical terms here to identify these plates. Don't worry about that. All we're doing is connecting a battery to liquid water. There's some acid in here that helps electricity flow, and if you do this, you'll start to see bubbles form from each of these wires as electricity flows through the liquid water. And if originally these test tubes were filled with water, the bubbles of gas would start to push out the water. Hey, the oxygen, that's the name of this gas, is less than the hydrogen, the name of this gas, filling up the test tube. It's not quite twice as many, but you would suspect that's probably what the ratio should be, right? Water consists of 2 H's and 1 O, and so if one test tube is being filled with the H's, another one filling with O, you'd expect 2 H's for every 1 O. Turns out, yeah, you're putting oxygen gas in one test tube and hydrogen gas in the other. So is this a physical or a chemical change? Chemical, right. We have H2O. See if I can write here on the screen, H2O. And that's turning into oxygen. Well, what's the chemical formula for oxygen gas? That's something I don't expect you to memorize, at least not yet. Turns out it's 2 oxygens stuck together, O2. Hydrogen gas, they also like to pair up in the natural state. It's H2 gas. And so if you have the chemical formula, you can clearly see, hey, it changed. Start with a bunch of H2Os, and now you have some O2s here and some H2s here. That must be a chemical change. Cool. All right, that's all for now. Thanks for watching.